Hi. All right. First virtual lecture today. Today I want to talk about simple harmonic motion. What is a simple harmonic oscillator? And then tie in something that you've read about, or I should say rather took notes on the video about, period, frequency, wavelength, and wave speed. So the first thing, what's a simple harmonic oscillator? There's lots of things in nature that oscillate. That means that they repeat some pattern, they repeat some behavior at predictable intervals. We're going to mostly focus on sound waves, but here's a couple that are really simple ones, right? We've dealt with something like this. If I just put a mass on a spring and I disturb it from, like equilibrium right here, it will oscillate above and below that equilibrium position. So this could be a simple harmonic oscillator. And again, in beginning physics, we love masses on springs. So there's lots of problems that deal with situations like this. The other one, maybe even more famous or more traditional, would be a pendulum. One of our earliest timekeeping devices would be a pendulum, right? It swings back and forth based on its length and maybe its mass, maybe how far I pull it. We're going to discover that predictably. So both of those would be simple harmonic oscillators. Technically, what does it mean to be a simple harmonic oscillator? It means its repeatability, some aspect of repeatability can be modeled with a sine curve. And let me show you what that might look like. And you have to use your imagination for this a little bit, and then I'll show you with me as an oscillator in a moment. Here's a different one, right? If you notice, I just put a pen on here, and this is just to illustrate or give you an idea. If I had the pen going up and down like this, right, that might be a little bit fast. Let me just see if I can put on that one. Obviously, the mass affects the period and frequency of this. Imagine this one. Not going smooth. Not going smooth, Hennings. Let's see if this one will work. I put a pen on this. And again, this is just for, mental concept models here. Pen's going up and down, right? I don't see necessarily a real obvious sine curve pattern there, but if I can get that pen facing in one direction, right, and it's going up and down, right, like this, and I bring a paper just sort of moving here, can you imagine the pattern it's going to leave behind? It's going to leave behind some wave-like pattern. So oftentimes students will say, oh, we're studying wave, but why are we dealing with pendulums and masses on springs? Because mathematically they can all be described in similar ways. So now we got an idea of what an oscillator is. Let's turn our attention to what we've been reading about, what I'm going to have you do for your homework assignments. Let me get rid of this stuff. And we'll review a few things here. Definitions, really important definitions from the video last week. Oscillators are always going to be defined by two pieces of information. Something called the period, right, which in physics is usually capital T, and it's simply the time for one complete cycle. So identifying what a complete cycle is important, and then it's just how long did it take for that cycle to occur. The units would be in seconds. Sometimes we might say it's seconds per cycle. Frequency is also a word that we're familiar with and we've used quite often. But frequency is just defined as cycles per second, and sometimes you can say it like that. How many cycles per second? But there's also a unit for that. A cycle per second is equivalent to a hertz, which is usually abbreviated Hz. Can you see red on there? Not very well. I'll use dark ink from here on out. And then finally, we've also have this idea of wavelength in meters. If it's measured in meters, just because it's about a wave, don't think that there's some new idea of a distance. It's just a distance from how far from here to here. It's going to be measured in meters using the SI system. So what I want to tie together is how does this wave speed equation, which we've learned about and which we're going to practice problems with, how does it tie in and where does it tie in with our basic concept, our basic notion of speed? So we'll pick up with that. This doesn't need much description to you, right? Speed is a really easy concept. It's the first thing we studied in this class, and it's simply distance divided by time. So if we're talking about a wave speed, we're not going to have a new definition of speed. It's simply how far does something move and in what time does it move? Does it travel that distance in. So even though the equations and the variables, we're going to use lambda and f and t, may look different, it's still just a speed. And let's see if we can connect how we see distance divided by time with our two versions of the wave speed equation. Right? Let me erase this. So here I've got this dashed line. That dashed line represents equilibrium. Will this be dark enough? Not even close to dark enough. That's probably dark enough. And I'm going to be the oscillator in this case. So what does it mean? Like a pendulum or a mass on a spring, I'm just going to move my hand up and down. While I'm moving my hand up and down or oscillating, I'm also going to walk this way. Right? I'm going to be really nerdy. I'm going to be about it. I'm going to actually take some data while we're doing this. I'm going to figure out the time that it takes for me to move from this point here to somewhere over there. So I'm going to go ahead and try to get my oscillations down. I think I got a nice one here, and I'm going to go. Can you see that? I hope it shows up on the video pretty well. I'll just go ahead and outline it in black. Be real careful here. That shows up a little bit better. And that took me really close to 4 seconds to do that. So the time would be 4 seconds. So if speed is distance divided by time, the old way to calculate speed would just be, what's this distance, right? Because if I'm kind of surfing this wave, if I'm traveling from this point to that point, I went some distance to do that. And of course, you know me, I got my meter stick, so let's just approximate it. I started here, and I'm going to end, we'll figure it out here. I'm going to end over here at that point. So that's actually it's almost exactly a meter and a half. Yeah, that's not bad. So my speed calculation would be 1.5 meters divided by 4. Right? So what is that? 1.5 divided by 4. With all the video stuff going, simple math eludes me. I bet you're going to know it. You're going to go, why are you using a calculator? But I'm going to do it anyways. 1.5 divided by 4. Hey, 0.375 meters per second. And I'll leave that down here. And again, we didn't need to know anything really about waves to do that. You just saw me. I started at this position. I went 1.5 meters, and I ended at this position. It took 4 seconds. So the speed was 0.375 meters per second. But let's think about what happened for the oscillation part. If you think about that, what did I do and how far did I move for one complete oscillation? That's important to know what it is. What is a cycle or one complete oscillation? It's a complete up and down motion and back up, or a complete wavelength has been generated. So if you think about this, what did my hand actually have to do to make this? It went up and it went back to equilibrium, but it didn't make a complete cycle. So a complete cycle would be going up and down and then returning back to equilibrium. So what did that look like kind of in slow motion? Up, all the way down to the low point and returning back to equilibrium. Well, that should look familiar. That's a distance between every other node. Right here, not here. That's not a wavelength. This is a wavelength. So I could identify this as lambda. That's a distance. Also remember, my waves aren't perfect, but this is pretty close. Crest to crest could be lambda, and trough to trough could be lambda. And so what happened in that sense? Well, the wave moved for just one oscillation. It didn't go the full 1.5 meters, right? It went this distance. It went a wavelength. And now let's also think about our vocabulary words. How long did that take? Well, by definition, the period is the time for one cycle. Right? So let's just think about that. In one cycle of time, I've moved 1 lambda of distance. So our speed equation is the same. It is distance divided by time, except now when we're dealing with the oscillation aspect, we do it this way. It's usually lowercase v for wave speed, and it's distance. But now we're talking about a wavelength, lambda, and it's divided by time. Well, it took a defined time, the period, to go one distance, lambda. So that would be one way to write the wave speed equation. The units for that would be meters per second. Now there's also always a defined relationship between frequency and period. So frequency and period are the inverse of one another. If you know one, you know the other. So I might write frequency is just 1 over period, and I could also write over here, well, period is 1 over frequency. So if I substitute in for t, for period, and write it this way, now you see where we're going to get that second expression, which is actually equivalent. I'm going to write it back over here, right? It's v is lambda. I've got a fraction in the denominator, so we do the reciprocate. So it's going to be lambda times f. So the point of this video is just for you to understand when we use the wave speed equation with these new looking variables, lambda and t, lambda and f, it's no longer, it's still just speed. It's still just a distance divided by time, except we're using characteristics of a wave or of an oscillator to define that speed. And that's what you're going to do with your homework assignment. You're going to start it off, first of all, by looking at some oscillating information or data about oscillators, and you're going to first calculate or be able to calculate what are the periods and what are the frequencies. We'll move into the wave speed and focus really more on sound waves in the coming days. All right, guys, so go back to Google Classroom, look at the problems that were assigned, and give those a shot, and I will see you at the Google Meet tomorrow, right? Google Meet tomorrow, 9 to 5. Everyone's going to be there. All right.